Okay, the last presentation will be given in English by Rui Yao. I hope he's with us. So let me try to. Okay. Just let me say the title of the talk: a ride-sharing simulation platform that considers dynamic supply-demand interactions.
Okay. So hi everyone, my name is Ray. I'm a PhD student under the supervision of Professor Shlomo Bekhor. Today I'm sharing with you our development of a ride-sharing simulation platform, which explicitly considers the dynamic driver supply, passenger demand, and their complex interactions. So let's now start with an illustration of ride-sharing from the perspective of a passenger. And I'll give it a taste on possible interactions between all the relevant parties. Now let's look at a passenger, Roy in this case, who wants to travel from the airport to the university. He requests a ride-sharing ride, and the platform provides him the estimated arrival time based on, let's say, current demand, supply, and traffic in the region. And Roy is good with the estimated arrival time, and so he chooses to proceed. And the platform just matches him with the driver who is estimated to be 7 minutes away from him. And suppose everything works, the driver pick up the passenger and finish the trip. Everyone's happy. But it gets a bit complicated when things do not go as planned. Suppose due to heavy traffic congestions, the driver got stuck somewhere on his way to pick up the passenger. And Roy has already waited for a long time. He doesn't want the service anymore and just chooses to cancel the trip. So consequently, the platform needs to reroute the driver to his next pickup or drop-off location, or reassign him with a new passenger. And conversely, if the driver thinks he cannot, or maybe just doesn't want to complete the trip, he can also choose to cancel the trip. And in this case, the passenger can decide whether to reorder a new ride or choose a different mode. So what we just shown is a simple one passenger example at a specific time, but things are getting even more complicated when considered in the dynamic environment, like in our real world operations. So for service platforms like Uber, Lyft, and Didi, the exact driver and passenger requests typically cannot be non-events because they're on-demand service. The new requests continue to emerge during the ride-sharing process. And this is a realistic setting of the real ride-sharing operations that new passenger driver can enter the system at different times. And the platform needs to determine or dynamically match the drivers and passengers together, even they didn't enter the system at the same time. And what's more, a driver who has already matched with passengers from the previous matching routes, for example, the driver already has someone to pick up, or even with onboard passengers, they can still be matched again with the new passengers. And this is related to the multi-passenger setting of ride-sharing, in which we like to utilize the empty car seats with the overall system efficiency. But this brings additional complexity to the problem, specifically for passengers who are already on board. Their drop-off times may be delayed due to the driver detours to pick up the new passengers. And for passengers who are already waiting for pickups, the waiting times may be longer. So similarly, the driver can also not non-events their exact trip characteristic, like the number of peer passengers to be picked up or travel with him, and the travel distance, travel time of the overall trip. So as we see here that these explanations, there exist complex dynamics and uncertainties in ride-sharing operations, and this could result in different driver and passenger actions. For example, driver or passengers may cancel the order because of a long waiting time before being matched with the driver, meaning he's keep waiting for a response from the matching platform, and the platform just telling, wait, I'm finding you a driver. Or because of a delayed pickup after being matched. And similarly, the driver can also cancel a matched passenger due to delays. So these cancellation actions may affect the trip of other passenger as well in a multi-passenger setting. And this could also trigger the train cancellation reaction. For example, based on the shared cost concept that, let's say for 1 kilometer is 10 shekel, but if you have more passengers, the cost will reduce for each one. So as we see that, and these complex interactions, it's important because in order to better understand the effect of driver supply and demand, and to design more efficient ride-sharing service with better real-world performance, it's necessary to consider these dynamic supply interactions. And to do so, we develop a ride-sharing simulation platform that accounts for all these elements in a realistic ride-sharing setting by incorporating dynamic supply demand, multiple passengers, cancellation before and after being matched, matching option acceptance and rejection. So these dynamic and cancellation rejection actions require development of new simulation events, procedures, and modules, such that it can provide detailed time-varying dynamic process of a ride-sharing system, and allow design and evaluate different operation strategies under more realistic settings. And our simulation platform follows the agent-based modeling approach. Here we show the overall flow chart for the ride-sharing simulation process. And as we can see, as we mentioned before, we develop new simulation events, procedure, and modules. And so specifically, we introduced the ride-sharing matching events that are associated with the service platforms matching candidate drivers and passengers. And our platform has the ability for testing and evaluating different operational strategies by allowing customized operational modules. And while the matching option, accept and rejection is handled within the agent matching response module and allows implementation of different matching option choice models. The reschedule event is executed once any change has been detected in the ride-sharing schedule. And in this case, the driver and passenger will be asked about their decisions regarding to the changes, if they want to cancel the order or even to leave the ride-sharing system. And this is related to the agent decision module, which simulates the decisions with some customizable decision models. And apart from the agent decision making due to changes in schedules, the agent staying or leaving decision-making events are introduced to capture agent cancellation before being matched, in which the agent decision module is also used. And we further increase the viewer for detailed explanation and implementation to our preprint of this research on the archive. So here we show our numerical experiment setups for illustrating the logical needs of simulation platform and the capabilities to handle the matching, option, acceptance, rejection, and order cancellations. We conducted the experiment using the well-known Winnipeg network with 150 some zones, more than 1,000 nodes, 2,500 links, more than 4,300 OD pairs, and the total hourly demand of the Winnipeg matrix is more than 55,000 trips. So in order to perform the simulation, we divide the static hourly demand into 4 15-minute period demands. Each consists of 10, 40, 40, and 10% of the hourly demand. And as the default setting, we assume 2,000 ride-sharing passengers and 1,600 ride-sharing drivers, and that uniformly sampled at random from the period demands. Here we select a driver agent from the simulation experiment to demonstrate the behavior of our ride-sharing simulation platform and showcase the matching option acceptance, rejection, and order cancellation actions. So initially, the driver leaves his origin at 824 and plans the background, as we can see here. And at 828, the driver decides to accept a ride-sharing passenger request, set himself online on the service platform, and immediately receive the matching option for picking passenger A and B at here. So he chooses to accept both of them because he has time. And now he's on his way to pick up the passengers using the green route. The drivers then pick both passenger A and B here. And now it's on his way to drop passenger A here using the orange route. The trip of the passenger A was completely successful And now the driver the purple route to drop the passenger B off. Now comes the interesting part, which also demonstrates the capabilities of our ridesharing platform. So at 8:50, the driver received matching options for picking up passengers C, D, and E. But he only chooses the step pick up passenger E, only to choose this one. These two are rejected. I mean, this is reasonable since for picking up passengers C and D require the driver to go back. This may be good in terms of system objective, for example, a minimum VKT of the overall system or maximizing the matching success rate. But for the driver, he doesn't care. This requires him to go back. He doesn't want that. So what happened under the hood is that a rescheduled event was called for the modified matching option for picking up only passenger E, and the itinerary was computed again. And it happens to the system that the route is same because the driver needs to drop off passenger B anyways, so the same route. And again, at 8:52, for some reasons, passenger E decides to cancel his order. So no more picking up passenger E here, but the driver still needs to drop passenger B anyways, so continue on the purple route. And the passenger B is dropped off, and the driver now is en route to his destination. So at 9:01, the driver set himself offline and reached destination, finished the trip. So this example illustrates the capabilities of our simulation platform, and our platform has reasonable behaviors. So in the previous slides, we showed the example of an individual driver agent. Here we show aggregated time series results in static profiles for passengers and drivers respectively. As we can see here, the most of the passenger and driver demands appear in the simulation during the second and third period as we specify in the simulation setting. They appear mostly during these periods. And as the simulation progresses to the right, the travel lane, the blue one here, and waiting for matching passengers, the red one here, gradually decrease. As you can see, the gradual decrease, and a switch to finish ride, green, or quit ride sharing, or the yellow one. And one thing to notice that the number of waiting for matching passengers, the red one, remains almost constant during this region. And this could be because a lot of passengers could not find a matching under such supply and demand condition at this specific periods. And similarly, as the simulation progresses, the driver gradually arrived at the destination, the green ones, and finish their trip. And as we can notice that the increase of number of drivers finish the trip, the slope here, is almost the same as the total number of increase of drivers, the outer slope here. And one explanation is that the driver trip length is too short, as we see in the numerical setting. And this result is also consistent with the literature that the ridesharing success rate is low for short trips. And that's also why a lot of passengers cannot find a matching and quit the service. Here we further show some sensitivity analysis regarding to different level of driver supplies. And one of the key operational parameters, the matching window here, matching window and number of drivers. So for a given demand level, 2,000 passengers in this case, when the supply level is low, as we can see here, the overall success rate, the yellow curve here, it's low, so it's low. And as the supply level increase, the overall success rate increase as well. But after some point, in this case around 2,000, the overall success rate starts to drop. And this is because many drivers cannot find matching. Since 2,000 drivers and 2,000 passengers is almost 1-to-1 ratio already. And the most interesting of all this graph is this one, that increase of matching window could result in a decrease of percentage VKT savings as the matching window increases. Intuitively, one may expect that with a larger matching window, more drivers and passengers can be considered matching process. So we're expecting high quality matching that's high VKT saving. And one extreme case that we can think about is the static case in which all the demands and supplies are non-events, and theoretically we can compute optimum value. So we're expecting the VKT could be much better, the saving could be better. But this might not be the case in reality, considering the dynamics and the interactions. Say that the service platform takes long time to find me a matching, I would just lose patience and leave the ride-sharing system and choose a different mode. So the result we get here is actually behavioral reasonable, but it's only possible to observe this kind of results if we consider the agent consolidation behavior. In other words, the demands and supplies are no longer exogenous fixed demands, but they're endogenous considered in a model in a dynamic manner with behavioral considerations. And this is also a main objective of our model. So these results confirm the importance of considering the dynamic supply and demand interactions in the ride-sharing models. So to conclude our research, we developed a new simulation platform with ability to handle dynamic driver supply, passing demands, driver passing acceptance rejection or matching options, order cancellation before and after being matched. Our platform can provide insights on the detailed time-varying dynamic process of a ride-sharing system under more realistic settings, and offers additional flexibilities in accommodating different operation strategies with a new ability to capture the complex interactions, and can be used to design more efficient ride-sharing systems to have better real-world performance. And our sensitivity analysis further exemplifies the importance of these new abilities, but possible only by a new simulation platform. So for further research, our simulation platform could be extended to allow more service options such as right-hand.
טוב, אנחנו קיבלנו גם את המסקנות, אז הכל בסדר, ונצא עכשיו להפסקת צהריים. תודה רבה על ההשתתפות.